Alright, so welcome to another video on vector calculus. In this video we're going to be introducing the concept of a line integral. So this concept is more general, it's not just exclusive to vector calculus, but it is also quite common in multivariable calculus. The idea is we're going to take a function of several variables and we're going to integrate it with respect to some curve. So this is some arbitrary curve C, which is defined by a function of y, actually a function of x, but y is a function of x, and then we integrate with respect to this arc length ds. Now if you recall from single variable calculus, you know that the arc length of a curve is basically given by the integral taking over all the sum of all those little arc lengths along the curve. In this case we're actually integrating a function within that arc length. So what we're going to do is we're going to zoom into this function here, and at the infinitesimal level we have the following right angle triangle. So basically the increment in x is determined by dx, increment in y is dy, and then the hypotenuse is ds, which represents the infinitesimal change in the arc length. Now using simple Pythagoras' theorem we can derive the following expression. So we have an expression for the arc length element in terms of dx and dy. Now in these cases what happens is that you're actually integrating a function of multiple variables, but the line integral in itself is defined as a single integral. So how are we actually going to do that? Because you cannot really integrate a multivariable function with respect to just one of them. You're not going to get a numerical value, which is what you usually want from a line integral. So what you're going to do is you're going to choose some parameter t. So you're going to parameterize the curve such that all the variables can be expressed in terms of another parameter t, and that way you can actually replace this by a function of a single variable. So if we take this expression and now we divide it by dt squared, what we find is that we get this expression right here. So we can group the terms like this, and then if we solve for the arc length ds, we get the following expression. So we have dt, now we're integrating with respect to the new parameter t, and then we have this element here which is basically multiplying dt, which is the first derivatives of those two variables squared. So we could easily write this in the following way. We can write the curve in terms of that new function. So now x and y are both functions of a parameter t. And notice that usually we just call the parameter t, but we can call it anything else we want. It doesn't have to be t. Now we have this part here, which is going to be a square root of dx over dt squared plus dy over dt squared. And we're going to integrate that with respect to the arc length. Actually not ds, dt in this case, because we made the substitution here. So this is how we would go about integrating. And you can imagine that you can extend this to further dimensions just by adding more variables into it and then expressing those new variables in terms of t as well. And then you would also add more terms to this square root here. Okay, so the question you may have now is, how do we actually find that suitable parameterization? Well, it really depends. There are three main cases that we need to take into account. So I'm going to show you what they are. The first one is for when you have just a function of a straight line that goes from point, let's say we have a point A to a point B. So when we have a straight line segment, we can actually parameterize that line in terms of some parameter t by doing the following. We're going to have an initial point A, and then what we're going to have is we're going to have 1 minus t times some vector, and this one is going to be a vector that points from the origin to point A, and then we're gonna add the parameter t times a vector that points from the origin to point B. Now you know that because this is a vector we can decompose it into x, y, and z. So basically we would take the coordinates of those 2 points and then we would have a set of 3 equations, one for each of the coordinates. And the really interesting thing about this one is that the limits of integration for some reason always become from 0 to 1. So when you make the substitution of that into that t, basically your limits of integration are always going to be from 0 to 1. And remember that a line integral is in essence a definite integral, so you need to have some limits of integration. I'm not going to go into the details of why that is, but this is just a general rule that we need to follow. So this is a standard parametrization for a straight line between 2 points. The next one is going to be for when you have some kind of circular arc. So let's say you have an arc that goes like this. Then you know that if it has some radius r, then you can parameterize this in the following way. Let's say that the angle is t, and then you can write r cosine t, and then y, you can write it as r sine t. And in this particular case, the parameter t, the boundaries of integration or the limits of integration, would actually depend on the angle itself. So basically we would have something like t1 and then t2. So it really depends. If for example, if your arc is going from this quadrant all the way to the second quadrant, then the limits will go from 0 to pi radians and so on. So it really depends on what chunk of that whole circular arc you're taking. So this one is also quite common. And the final one is for when you have a function explicitly as a function of another variable. So for example, y as a function of x. So this one is also quite common. So in that case, what we do is, well, x is the independent variable, so how about we just call it itself, and then that way y is just going to be a function of x. And you notice that, well, now we have the two variables are both functions of a single parameter x. So in that case, it becomes quite easy to do. So in that case, the parameter would actually go from whatever the limit is on x. So we would have from a to b. So those are the three most common parameterizations that we're going to be using. So that is it. That is basically the essence of line integrals. And in the next video, I'm going to start showing you some examples, and we're going to look at the different cases and how we can combine them and some of the other properties of line integrals.